So this video will be a discussion of number 1 from the 2017 AP Calc AB and BC exam. It's a question that involved the use of a calculator, and if we get right into it here, they provided us with this table of values. And so the independent variable h is measured in feet, and you will notice that we don't have h every 2 feet. It's kind of scattered, right? So the first delta h is 2, then a delta h of 3, and then a delta h of 5. And then we have area calculations. And if you read the problem statement, a tank is 10 feet tall, and the area of the horizontal cross sections of the tank, h at a height of h feet, is given by these values within the table. So at the bottom of the tank, the area of the bottom is 50.3 square feet, but then the area of the cross section at the very top of the tank is 2.9 square feet, and then we have the area at two values up the tank, 2 feet up the tank, and then halfway up the tank, 5 feet up the tank. Tells us that A of h is measured in square feet. That's obvious from the table. Function A is continuous and decreases as h goes up, so A is a decreasing function, and we've got those selected values of A of h in the table. Now part A asks us to use a left Riemann sum, 3 subintervals indicated by the data in the table to approximate the volume of the tank, indicate units of measure. So what I did real fast, just to kind of make sure I was on the right track with everything, I thought about finding the volume of a slice of the tank. So if I took a horizontal slice of the tank, to find the volume of that horizontal slice, I would need to know the area of the cross-sectional face of that slice, and then times the thickness of it, which is a tiny, tiny change in height. So that would be the volume approximately of one slice of the tank. Well, I want to add together a bunch of slices, so I'm going to let the definite integral do all the work. I'm going to have my formula for the area of the cross sections, A of h, as my integrand, and then the delta h is going to become a dh. I want the volume of the entire tank, so the tank goes from a height of 0 feet above the ground to a height of 10 feet above the ground, and I'm doing a left Riemann sum. So I realized, all right, well, my first interval goes from 0 to 2. The left endpoint is 0, so the height of that first rectangle is going to be given by the area of the base of the tank, and then the width of that rectangle is 2 units. So I proceeded across the rest of the x-axis with that same mentality. My next subinterval goes from 2 to 5, so I've got a width of 3. My left endpoint is 2, so I'm taking the y value or the function value at 2 to generate the height of that rectangle. And then my last rectangle has a width of 5 and a height given by the y value at the left endpoint of this interval, which is 6.5. And then the calculator's in play. Fire this into the calculator. You've got 176.3 cubic feet. It did say to indicate units of measure, so don't overlook little things like that if it ever applies. In part B, we are asked about our approximation from part A and to try to decide if it's an overestimate or an underestimate. Well, you saw this little sketch in part A, and it's pretty obvious that our rectangles accumulated too much extra area. Now, the reason for that, you're going to want to make a statement about some of the conditions within the problem. So the reason why we have these left Riemann sums accumulating extra area is because the function A of h is decreasing. So since A of h is decreasing and positive, a left Riemann sum is going to accumulate too much area and give us an overestimate for the value of that integral that we were approximating. So that was pretty quick, pretty simple in part B there. Part C is a situation where they suggest a new way to model this function A of h. So the area in square feet of the horizontal cross sections at h feet is modeled by this function. So they've gone from the A of h values in the table to this new formula for the area of a cross section given by f of h. So h is still the independent variable, so the area of a cross section still depends on the height up the tank from which we take that cross section. Based on this model, find the volume of the tank, indicate units of measure. So same starting point as part A, right? I need to find the volume of a slice first, so I'm going to have the area of a cross section times the height, giving me that. I'm going to let an integral add together a bunch of these individual slice calculations, and if I integrate my formula for the area of a cross section that I've been provided with here in part C, which is f of h, The calculator's in play, so I can carry out everything on the calculator from there. So here's the input to a TI-83 math menu function integration tool, and you see the answer rounded to 3 digits beyond the decimal is 101.325. Again, units of measure, make sure you tack them on at the end, cubic feet. Part D is definitely the toughest part of this question in my opinion. They tell us that water is pumped into the tank. When the height of the water is 5 feet, the height of that water is increasing at a rate of 0.26 feet per minute. So what I realized right away was that that's the rate of change of the height. Since it's increasing, that rate of change is positive. So that allowed me to define this value right away. The rate of change of the height of the water in the tank with respect to time at a height of 5 feet is 0.26 feet per minute. If you read on, using the model from part C, find the rate at which the volume of the water is changing with respect to time when the height of the water is 5 feet. So I want to find the rate at which the volume is changing. So I want dV dt, and I want dV dt at the same moment in time, so when the height of the water in the tank is 5 feet. So that's the question. So here's what's really, really sneaky about part D. They don't provide us with a volume equation anywhere. They provide us with this formula that gives you the area of the face of a cross section, h feet up the tank. So this is copy and pasted from out of part C. If I'm trying to come up with a formula that relates V and H, the volume of the tank is going to be found by doing the same sort of integral that we did in part C, but this is sort of weird because we don't want the volume of the full tank right now, right? The volume of the full tank required us to go from 0 feet for our height clear up to 10 feet. We want the volume of the water in the tank. So that's going to depend on how high the water level is. So this integral has been manipulated to just go from 0 to h, and you will notice I took the function f, but I swapped out the variable. My variable h is that upper limit of integration, so I'm going to have to kind of pick a dummy variable to replace the variable h in the function that represents the area of the face of one of these cross sections. And you see that that is also the letter I put within this differential. So what am I going to do to generate a dV dt? Well, I'm going to take the derivative of the left-hand side with respect to t. So the derivative of volume with respect to time is just dV dt, but then I'm going to have to take the derivative of this other side with respect to t as well. So if I take the derivative of this definite integral, I'm going to replace the holding variable, the dummy variable, with that upper limit of integration. But then because h changes over time, I have to use a little chain rule and finish off by multiplying by the derivative of my inner function, multiply by the derivative of h with respect to t. Since h isn't constant, the height of the water in the tank changes as the water level rises. So it's an application of FTC Part 2, and then it's finished off with a little chain rule. From there, it's pretty straightforward. You want to know dV dt evaluated at h equals 5. So putting 5 in place of the h here is going to just be an evaluation of f of 5. You can do that on the calculator. And then dH dt at that same value of h is 0.26. This is an area calculation, so this is measured in square feet. Units of this, feet per minute. So the units of the product is going to be cubic feet per minute. And this answer is, again, arrived at just by plugging this into the calculator and multiplying by 0.26.